Okay, question one. Here's my drawing and force diagram, so we'll just go straight in with the working. So up equals down tells us that the reaction at x is equal to 0.75 G. Right equals left tells us that 0.6 times the reaction at x equals the reaction at y. So the reaction at y is 0.6 times 0.75 G, which is 0.45 G. And finally we'll take moments about x. Typically you do want to take moments wherever you've got two forces, and this time there's two forces that act through x. So moments about x then, if we look at the weight first, so the weight is a force of 0.75 G, and the perpendicular distance from x to the line of action of the force is, if we call the length of the stick L, then it's L over 2 cos theta. Now, the counterclockwise moment comes from the reaction at y, so this time the force is the reaction at y, which is 0.45 G, and the perpendicular distance, well here the line of action of the force continues here, which means we want this distance here, which is just the height from the ground to y, which is going to be L sine theta. Now here you see that it doesn't matter what the length of the stick is, because we can divide both sides by L, we can divide both sides by G, and we can even divide both sides by cos theta to get 0.45 tan theta equals 0.375. So our final answer then is to do theta equals inverse tan of 0.375 over 0.45, which is 5/6, to give theta equals 39.8 degrees. This one you should give to three significant figures because it was independent of G. The G's cancelled here. Now, the reason why this is the smallest possible angle is maybe not immediately clear, but allow me to explain why. What we've done here when we've set the right force equal to the left force is we've said that the friction force is actually equal to the reaction at y. And if we make the assumption that it's in limiting equilibrium, that means that the friction is at its maximum value here. And so what will happen then is, if we were to push the bottom of the stick closer to the wall and therefore increase the angle here, then it would actually be more stable. It would still be in equilibrium, but it wouldn't be in limiting equilibrium. Whereas if we were to move the bottom away from the wall and lower theta, well, in this case the reaction at y would increase, but the friction force was already at its maximum, and therefore it's not in equilibrium, and so the stick would fall. So that's why this is our answer to the question.